Works. All right. Well, it's been quite some time since I've actually given a lecture, so I hope you're all excited for one by me, and please ignore my lack of practice in giving these lectures. Yeah, so as you can tell by the first slide, these are slides that we presented last year during the beginner lecture series, and so there are a few changes to it, but effectively this is like basically 2 lectures worth of material, but I'm just going to get through as much as I get through, and if we get through one lecture, that'd be great, and we can do the other half on a different week. So the first half is on this concept called reinforcement learning, and then the second half is the thing in brackets, the word deep. And so maybe you can already be thinking about what the difference is between regular reinforcement learning and deep reinforcement learning is, given what you know about the naming conventions in the machine learning field so far. So you know there's machine learning and then there's deep learning. What was the change between machine learning and deep learning? That's the same exact change from reinforcement learning to deep reinforcement learning. So yeah, feel free to interrupt me. Hopefully no one's behind me. Yeah, so feel free to interrupt me at any point. I'm happy to discuss anything that we need, because we do have a smaller group today, so we can be a bit more specific to what you all want to learn more about. Does anyone know already what reinforcement learning is? Or has anyone heard of it? Okay, a couple people. This is good. This is good. So has anyone taken a psychology class, like maybe Psych 100 or something in high school or in college? Yeah? So have you heard these 2 words used together? Reinforcement and learning? Donnie, should I share my screen in the Zoom?
Yeah, you should.
Okay, I'm going to do that now.
Okay.
So yeah, so has anyone heard, oh no. I don't know why the aspect ratio is so weird. Okay. There we go. Boom. All right, this should work now. All right. Is good?
Yep.
Maybe I should do this. And okay. All right, good. So reinforcement learning is this term from psychology. Does anyone want to tell me what that is? Has anyone heard of it? Yeah, Mark, go ahead.
So I think the classic example is like Pavlov having like a stimulus or something that can cause someone else to start doing something. So I think the classic example is having food and then ringing the bell and then giving the food to the dog and then eventually just taking the food away and just ringing the bell to get the dog to salivate.
Exactly, yeah. So we're in the intuition and history part now. So what you just said is correct, Mark, but I'm going to let the slides explain it again. But what you said is perfectly accurate. So the first idea is we've all looked at supervised learning. That was lecture number 1, which is the idea that you have these input-output pairs, and you use those to train your models, right? You have an input, and you know what the correct output is. So examples of this are like regression and classification, which we've seen already. Contrasting to this, we have unsupervised learning, which is the idea where you have no labels, you just have a bunch of data, and you're meant to find patterns in the data. So this is like clustering or dimensionality reduction or all these other aspects where you have effectively like you don't know what the correct output is, but you do know that there's some patterns in the data, and you can use that to learn about the data and learn about the world around us. So now I ask you about something that doesn't cleanly fit into either of these things. So it's not that we have a solution for every given input. It's not that we have the correct output for an input. And it's not that we have no outputs. What if instead you can tell whether something is good or bad, but you don't actually know how to get there? So the idea is that you can tell, if I show you a solution, you can say, yeah, that is a solution, but you don't know what the actual correct output should be. Okay, that sounds kind of weird, but I'll give you an example now. So let's say I asked you all to use machine learning or whatever to get a robot to walk, right? You know what it looks like for the robot to walk. You can say, yeah, that robot is walking, or no, that robot's not walking. But you have no idea what the correct output for each of the motors should be for it to walk, right? Unless you're a really good robotics engineer and you can tell. So you would not know what the exact output of the machine learning model should be, but you know that after a series of these outputs, it should look like it's walking. So this is the domain that doesn't cleanly fit into supervised learning, and it doesn't cleanly fit into unsupervised learning. Does everyone see why? Because you don't know what the correct output is. You just know whether a series of outputs looked correct, right? And you can tell and assess how good they are. So that is what the field of reinforcement learning tackles. And so we're going to talk about what Mark mentioned. So there's this concept from psychology called operant conditioning, where you have some animals that have positive reinforcement introduced that increases the likelihood that the animal would do the behavior, and you have negative reinforcement that is going to punish the animal or whatever to reduce the ability of it to do that, or reduce the want of it to do that behavior. So this happens, you can talk about it whether on a conscious level or a subconscious level, but we can think about this, or we can think about machine learning in general as kind of doing this, where we defined previously like a loss function, and you would tell whether the model is doing well or not based on that loss function. Here we don't have a loss, but we have more of this thing called a reward function. So you can tell how good something is based on how much reward it gets. And we don't really think about punishments, we more think about negative rewards, if you want to think about it that way. So the relevance to UMass, and the reason that you must have heard this word a lot being students at UMass, is that Andy Bartu, the guy on the bottom, was a professor here. Now he's Professor Emeritus. And one of his PhD students, Rich Sutton, who's now at, I think, DeepMind in Montreal, or in Alberta, sorry. And they wrote a book together called Reinforcement Learning, which basically coined the term reinforcement learning and started the field effectively. And so you can think about this as like the magnus opus for all reinforcement learning literature. If any of you have gotten into RL research, this is the first book that you read when you're learning about reinforcement learning. It was written here at UMass, and so UMass is a very, very big reinforcement learning hub. So we have a lot of professors working on it because they all were postdocs or PhD students under Andy Bartu. So there was also the RL conference last summer here at UMass, which was the first ever reinforcement learning conference, which is about all papers all about reinforcement learning. And so it started to take off a lot, especially because nowadays even things like ChatGPT are trained using reinforcement learning. So
what year did this happen?
this book is the 2018 edition, which is the second edition. I think the first edition came out in like 1990 something, I believe. But they've been working on it. So Andy was a professor here up until I think 2010, and he started in the 70s, 80s, I think. So yeah, pretty old.
When did this reinforcement learning creation with this particular PhD happen?
I would say, I think it was early 90s. Yeah, I would say. Don't quote me on that. You could probably Google it and get a better answer. Okay, so this is the only condition you need to be able to use reinforcement learning to solve a problem. Well, almost, right? You need to be able to format your problem in this weird diagram. So I'll talk you through the diagram. It's pretty simple. You have an agent and an environment. So an agent is this thing that lives in a world, and then the environment is the world itself. So I hope you all believe that you're all agents and that the world is everything else that's not you, right? Some people might argue with that. So the idea is that as an agent, you can do a thing called an action. You can take an action, all right? And when you take an action, the environment responds and changes based on your actions that you take. So I have the action of I'm going to take a sip of this tea or whatever, and the environment will change in the sense that now the tea will be gone and it will be in my stomach, for example, right? There's also another thing which is called the reward. So the environment responds with two things. It responds with a new state, st+1, and it responds with a new reward, rt+1. So given that you start at a state st, you take an action at, the environment gives you a new state st+1 and a new reward, rt+1. Right? Those are the three letters you're going to need to know, is r, s, and a. Okay? Any questions about this diagram? Okay, cool. So yeah, so an agent interacts with an environment through a set of actions a sub t, and the environment responds with a reward r sub t in a new state. Okay, so let's just do like one really quick example. Can someone come up with an example of a domain where you might be able to use this thing? It's almost anything you say would be correct. Like any time there's an agent in an environment. Yeah.
Let's say a student in a school.
Exactly. Okay, so let's say you're a student in a school. This is a very personal example. And you have a series of actions. So like, let's just yell out like a set of actions that you could have as a student. Like you wake up in the morning and you have like 12 different options of things you can do. Like just let's say like 3 or 4 examples of actions you could take. Yeah.
Go back to sleep.
Go back to sleep. All right, so this is a very, very personal one. So you can decide, you wake up in the morning, first action is I'm going to go back to sleep. All right, first, cool. Second action, what's another action? take a shower. All right, start the day. All right, and let's say third action, I don't know, just one. We just need one more. Something more like, you can make your bed, yeah, first thing in the morning. Okay, awesome. Yeah, so you make your bed, you take a shower, or you go back to sleep. So, which of these would give you a higher reward? Now, this is a very important concept. So, of those three, which of them would give you a higher R value? I mean, this is maybe personal depending on what kind of person you are. You think make your bed would give you the highest reward?
Actually, no. Take a shower.
Okay.
The hardest.
So I know for me, going back to bed would give me the highest reward because I would immediately feel way better. So this is the thing we're going to talk about today, and I asked this more as a trick question because there's a difference between reward and return. Like return is a sum of rewards over your life. And maybe taking a shower would actually lead to better outcomes in the future because you'll go to class, then you'll finally graduate, whatever, and then you'll get like really good outcomes in the future. But going back to bed feels really good right now, but might not help you in the future. So we're going to talk about that. That's a really important concept. But so that's just one example. And the important thing about this is that you have a state and a state t+1, and the state encodes all the information you need to know to predict what the next state is. So this is called the Markov property, but we won't talk about that too much. Okay, so more formal example. How should a robot behave so as to optimize its performance, right? So this would be an example where you have a robot and its series of actions are like move this joint in this way, or move this joint in this way, or move this joint in this way. All those different joints, they have a lot of different actions they can take. And then they have a reward, which is something like 1 for every time step that you're walking for. Right? So you can just come up with some reward that's how good something is. And so anyone that's worked on robotics, you can actually use reinforcement learning to create the control paradigm for your robots. Another thing would be something like helicopter control. So how do you actually automate the motion of a helicopter? Same exact thing. You have a bunch of different things, like you either want to increase the speed that your propeller moves, or you have the other joysticks that I don't know what they do. And those are all your actions that you can take. And your reward is maybe how upright is your helicopter, right? So if your helicopter is upside down, that's probably not good. If your helicopter is right straight up, that's probably good. All right. And another thing would be, how do you make a good chess playing program? So this also counts as RL because you could hypothetically define a reward function, which is maybe how many pieces do I have versus the other team, or versus the other person. Do I have more pieces than them? That means I'm probably doing better than them, right? That's an example of a reward function you could use to play RL. So the point of this, the reason I give all these examples, is that you can make almost any one of your problems that you have, machine learning or anything, you can form them as an RL problem. Now, that's not to say you should do it, but you can do it. So, for example, anything we've looked at so far in the supervised learning could be reinforcement learning. So, like, how could we do it for like image classification? I want to tell if the image I'm looking at is a cat or a dog. How could I set that up as a reinforcement learning algorithm? And it is, yeah. Exactly. So you have your action, which is predict a label, and then your like reward is just 1 if you got it right, or -1 if you got it wrong, right? Exactly. So you can actually use RL algorithms to solve almost any machine learning problem, but usually machine learning solutions, if you have the labels, you should just use them directly instead of using reinforcement learning. But that's a tangent that we won't get into. Okay. Yes, we already looked at an example here. So as I was talking about, oh yeah, go ahead.
So I understand the like action and the reward, but like I'm still a bit confused on like what the state actually is.
Mm-hmm. So the state is a series of basically numbers that encodes everything you need to know about the world, right? So right now, the state for me is that my location is this like longitude and latitude. I am in Amherst, and then also where all of you are is also part of the state. And also like what's happening at my house right now, that's also part of the state. So like everything I need to know to make a decision is part of the state, basically.
So like for your chess example,
Mm-hmm.
would be like all the positions of the pieces on the board?
Exactly. It would be all the positions of the pieces of the board, and maybe even like the history of the board if I'm trying to learn from the other opponent and learn like what kind of strategy they take. So yeah, exactly. We can actually do this. So what would be the state for a robot that's trying to learn how to walk? Yeah. Yeah, exactly. The position of all its limbs. Maybe one of them would be like how upright it is. Maybe one of them would be whether there's obstacles around it because you might want it to navigate the obstacles. So these are all examples of that. Yeah. What about for a helicopter? What could that be? What would the state be for a helicopter? Yeah.
The speed of its blade.
Mm-hmm. Is that everything you need, or is there more that you probably? Yeah. That's one thing. Yeah. Mm-hmm. Elevation, and then also whether there's obstacles around you. things like that, the weight of the helicopter, et cetera, right? Does that answer your question a bit better? Okay, awesome. Okay, so a reinforcement learning agent's goal is to maximize not just its reward that it gets at every time step, but actually it's the sum of all the rewards that it gets throughout its life. So again, in the wake up and go to class example versus sleeping in would give me a higher reward right now because I'd feel really comfortable, but then going to school and going to class would lead to a higher reward in the long term because maybe I'd go and actually graduate and get a degree and then start working, whereas if I just slept all the time, I wouldn't get that, right? So you can think about this G sub t is just the sum of all the reward values from 0 to t of the reward you got at that time step. So throughout my life, however many time steps I live, it's weird to call it a time step, however many time steps I live, I'm going to sum the reward I get at every single time step, right? Everyone know this notation, the summation thing? Yeah. Okay. Now here's another question though. Does one reward 10 years from now, is that equal to one reward today? So if anyone here is like a finance student, you might know intuitively how to think about this, but would you rather I give you $1 today or $1 10 years from now? Yeah, today, right? Why? Does anyone want to put into words why? Yeah.
It has less value in the future, probably because the value of the dollar has gone down. Inflation.
So you can think of it in the actual economic sense that if you have a dollar in the future, there's going to be inflation, so it's actually going to be worth less than $1 today. You can think of it in the investor growth mindset, saying that if I have a dollar today, I could invest it, and then I'd have more than $1 10 years from now. You could think of it from the perspective of, I'm greedy and I want to buy an ice cream today. I don't care about $1 10 years from now because I want the ice cream today, right? So whatever lens you want to look at it from, it means the same thing. It means that future reward is worth less. So the way you do this is you include this thing called a discount, right? Which is used by this little Greek letter gamma. So if you see this little letter here, this is gamma. And gamma is less than or equal to 1. And it's called the discount factor. So the way you can get the sum of discounted future reward, also known as the return, is you just take the reward right now plus gamma of the reward tomorrow, or whatever next time step is, plus gamma squared of the reward 2 days from now, plus gamma cubed, reward 3 days from now, all the way to gamma to the power of t, the reward t days from now. Yeah?
So is it kind of like weights, like create a machine learning?
Exactly. You can think of it a weight, but the thing is, it's like a constant weight every single day. It's like, how much do I value the future over today? Yeah?
If I understand this correctly, so R0 is, let's say, today.
Yeah.
So how do you know the future?
Oh, you don't in practice, but this is basically looking back. After your life is over, you look back and you say, how good of a life did I live? And you take this sum over your life, basically. But another thing is that these RL agents are actually looking into the future because they're predicting what is going to be able to happen in the future, and they're taking that. It might not be an accurate prediction, but you are predicting. So for me, when I'm trying to get into bed, or when I'm waking up in the morning, I make a prediction that, okay, I know that right now if I get out of bed it's going to be bad, but in the future my rewards are going to be really, really high, so I'd rather get out of bed now than go back to sleep. So you're basically making a prediction about where you're going to be in the future, but that prediction you're slightly making it slightly worse because you don't care that much about the future, you care a lot about today. All right, this is really central, so I really hope this discount factor explains. So can someone tell me, just like a check, why does it have to be less than or equal to 1? Actually, in fact, it should be less than or equal to 1, bigger than or equal to 0. Why is that the case? Yeah?
Your value would just increase otherwise.
Exactly. Yeah, so if you have it like 1.1, then you would have infinite magnitude for something that happens at the end of your life, which is not really, it doesn't make much sense to have that. Why does it have to be bigger than 0, bigger than or equal to 0?
If it goes negative, it's like decreasing.
It's decreasing, but also weirdly because every other reward value will be positive because you're squaring or to the fourth. And so it's weird because then, I only care about the even time steps in my life. That's also odd. So you always just think of it from 0 to 1 because it's a discount factor. And so if you take this to the end, like to R infinity, the discount factor will be 0, right? Because 0 point anything, or any number between 0 and 1 to the power of infinity is going to be 0, right? Because it gets smaller and smaller and smaller and smaller. Okay. Cool, so let's just do a quick test right now. What happens if gamma is equal to 1? What does that mean? It's allowed to be equal to 1, but what happens if it is? Yeah?
All of your R's are the same value.
Or you value each of the R's the same, right? Yeah, exactly. So all of my R's I care about equally as much. So I would happily trade off $1 today versus $1 tomorrow because I don't care, provided they give me the same reward. Okay? That make sense to everybody? What about if I had a gamma of 0? What does that mean? That's also valid. You're also allowed to have it equal to 0. What would that mean? What is it? Well, look at the math here. One of them isn't worthless. One of the numbers, all the rest of them are.
I have no future reward.
Right, or you don't care about the future at all. You literally only care about today, right? Which sometimes that's how I am. Like I literally don't care about what's going to happen in the future. I mean, that's maybe never accurate, but I care only about the thing that's going to happen right now. Okay, so this is like the difference between myopic behavior, where you only care about the short term, versus really long-term planning behavior. Okay, everyone understand this? Okay, cool. Okay, so another question is, can't we just use supervised learning techniques to maximize this goal, where we have some kind of input and output? Well, we saw no, because we don't even know what the correct output should be. We have no idea what the best action is at every given point. We just know that after you've taken the action, whether that was a good thing or not to do. So how do you actually find the best action? Well, for this, we're going to need to define a couple of functions. So these are two functions that are very, very, very important. It's called the value function, or v of s, and the q function, q of s comma a. All right? So these two functions express very, very similar things, and they're very intimately related. But I want you all to look at this and try to understand what these things are. So the value function, value v of s, is the value of state s. Now the value, this is different to the reward that you would have gotten by getting to that state. The value is basically saying, in all the futures that I could ever imagine, how good was that state to have been in the long term? So like right now, me giving this lecture, that has a pretty high value for me. Not because it feels good right now, which it does, like I'm enjoying this, but also because long term, it's good for me to practice like giving talks or whatever. And so I'm incorporating the future in my estimate of the value. So the value of a state is basically saying the predicted future value of being in this state. All right? It's a bit of a weird concept, but I hope you ask a question if it doesn't make sense. So another thing is the q function, which is equally important, is saying the value of taking action A at state S. So it's very similar to the value function, but it's just saying I'm in this state and I do this. So maybe the value of me giving this lecture and also like drinking this drink would make me feel blah, would have this future consequence, right? So does everyone understand the difference between the value of state and the value of the q function at a state and action? So the point is the q function always takes a state and an action. Okay, so just a quick quiz. How could you get from the q function to the v function? Assuming that they're both correct, assuming that I actually can write down exactly what my q function is. For every action I could possibly take at this state, how could I find the value of this state? Is that this? Oh, yes. So I'll go back to this so you can look at them. If I know what the value of taking every single action I could possibly take from this state, what is the value of this state? So I'll give you an example. Yeah, do you want to say something? Okay, this is a really good option. So is it the average? So let's think about it. In my life right now, there's probably a million things I could do right now, like a million different actions I could do. You know, one of them is move my hand like this, one of them is move my hands like this, one of them is to keep talking, and these are all actions I can take, right? And the value of this state isn't the average over everything I could have done, but it's the best thing that I could do from this state. Does everyone see why it's the best thing? Because I'm only ever going to do the best thing for me in the future. If I have this estimate in my head about what the best thing for me to do is, I would do the best thing. I wouldn't do an average of all the things. I would do the best thing. So there's this equation here. This is kind of confusing, but actually we'll do this. So the value function, v of s, is just the max over all your actions of the q function. Okay, so all that says is that the value of this current state is just whatever the best action that I could take, the q function of that action. Okay, so the q value of the best action I could ever take is equal to the value of the state. Because I'm assuming I'm acting rationally, I'm going to take the best action that I'm going to take. All right, this is probably the biggest sticking point, is that, and then how this leads to this equation here. So think about my life, right? This here, q of s, is saying the q value of me being in this state and taking a certain action A. Now I want to ask you, do you agree that this is equal to, so this E means the expected value, if anyone hasn't encountered that yet. The Q value of taking action A in state S is the expected value of the reward that I would have gotten by taking that action in that state, plus the discounted maximum over A of Q S prime A prime. All right? So S prime and A prime are the, S prime is the new state that I turn up in because I took action A. All right? So it's like S t plus 1 in the diagram before. And A prime is this like subscript is saying like the maximum A value that I could have taken. So remember what I just told you. What is max A of Q of S prime A prime? Value of what? Which state? Is it going to be the value of S or the value of S prime? S prime, exactly, right? So you're right. So this here is saying that, okay, the Q value of today is equal to the reward that I got plus the discounted value of the future. Which kind of makes sense because right now I'm in this state. I take this action here. I'm now in this state. So what is the value of being in this state? Well, I just discount that value and then I add the reward that I got in that transition and then now I get the value of today. So you basically, the reason there's an expectation is because you're doing this over every possible future you could have. So I could do this and I could imagine that there's a bunch of different consequences of what I did and I'm going to take an average over all those consequences saying, okay, on average this gives me a reward of 3 and then I turn up to be in a state that has a value 10. So the value of today is 3 plus discounted 10, which we'll say is 13. Okay? So this is actually the new biggest sticking point. So this, I really want to make sure you all understand this. So if there's any questions at all, I'm going to have it on the screen for like 30 seconds and then just stare at it and see if you can come up with a question and we'll talk about it. So this, if you get this equation, everything that follows today will be smooth sailing, I hope.
Can you just remind me what the y is again?
The y? Oh, the gamma. The gamma here is the discount factor. So that's the number between 0 and 1 that says how much I care about the future state S prime versus today's state S. Yeah, Braden?
Why is it R of t plus 1 and not
This is just notation. R of t plus 1, I just called it as the reward I got next. So you can call it R of t or R of t plus 1. All it means is that it's the reward I got for taking action A in state S immediately, the immediate reward that I get. So if you imagine, let's just do this example here. I am trying to figure out what is the Q value of me being in state in bed and taking action, go back to sleep. Okay? So that's the example I'm trying to do here. So it's basically saying it's the expected reward that I get for doing that. So it's a pretty high reward for me going back to bed because then I feel good, right? So I have a pretty high reward. Let's say I get a reward of 10. And then I'm saying the discounted value of being in the back to sleep task. So maybe that's actually a really negative value because I wake up and then it's already like noon and I missed my class. That's a negative state to be in that has low value. So we're saying that the value of taking action, go back to sleep when I'm in state, just woke up, is equal to a really high number, R of t plus 1, because I get a really high reward, plus a discounted really low number. So it actually turns out to be not that good of a thing to go back to sleep because this value is really low of being in the future. But the reward I get immediately is pretty high. So this actually incorporates, you can see how this now takes into account the future in your outcomes. It's obviously discounted by a factor gamma, but it is taking into account. All right, any other questions? Yeah?
So, like, how are you like calculating the max of like the state in action? Like, are you assigning like a number value for every state in action? How do you like know what the best value is?
Yeah, great question. So the easiest way to do this is you represent your Q function as a table. So it's called tabular RL. It's what Sutton and Bartu talked about in their book. But tabular RL basically means I can write down for every state and action a number. So I literally have a table in your spread, like you literally store in your code a table that says for every state in the world, there's every action. Now obviously, that's not possible in the real world because you have infinite states and infinite actions, and that's why we're going to get to the deep RL later. But for now, imagine you can write down every state and every action. Okay? Yeah?
So while you're trying to compute the best value for like the next second step, instead of thinking the step we're going to take, because right now we're taking the expected value of RT plus 1, and that's like the every possible way of doing the next step.
So this is right, but the important part is that once I end up in state S prime, I'm going to take the best action that I could have taken from S prime. It's not an expectation over all the actions I could have taken. It's actually, I'm going to take the best. The thing that the expectation is over, I could have made this more complicated to answer your question. Not more complicated, but I could have made it more specific, because the expectation, I didn't say what it's over. This is the expectation over future states S prime. So it's not over the actions, it's just over the states. Yeah, so it's basically saying, whatever state I turn up in, what's the best thing I could have done from there? It's not saying the average thing that I could have done at the average state that I could have done, right?
And then you can just compare every step.
Exactly.
Or every action and then find the best one.
Exactly. And then you find the best one, and then you say, okay, that's what I would have taken at that state, multiplied by the probability of me ending up in that state, plus the reward, et cetera, right? That's a great question, though. Okay. Yeah, Nico.
Does the value or magnitude of the Q function drop off as you get further down the process?
That's a really good question. The value of the Q function doesn't, because, well, technically yes, because the Q function itself encodes the future value. So the Q function will never get smaller, because it's always going to encode the future starting from some given point in time. But the discounted Q value will for sure get smaller as you get there. Because the Q function is basically saying, being in this state right now, what is the value of me taking this action right now on the future? Like in the full sum of the future. Okay, any questions here? All right, so equivalent, and I hope this makes sense that this is equivalent, is that the value of a state is just equal to the expected reward you can get from the state plus the discounted future value. So this is getting into your point here, where you're now having an expectation over all the actions you're going to take, which I assume you're going to take the best action here, so actually there should be a little max here, because you're taking the best action. But this is the very equivalent. All right, so there we go. All right, so now you now have all the background that you need to understand the most powerful introductory RL algorithm called Q learning, which, can anyone guess what it does? I'll give you a hint. The two words of the things that it does are in the name of it. It learns based on the Q, right? Or in fact, it learns the Q and also learns based on the Q. It does both. So now that we know what a good Q function looks like, how can we actually learn it? Well, what we can do is we can actually incrementally update our Q functions such that they follow this pattern. So we know now that the Q function should follow this pattern if we have the correct Q function. So what we can do is we can just incrementally update our Q functions until we get them to satisfy this equation here. So pretty easy, right? Just you wait. So this is how you do it. This is the most important equation for Q learning. It's super daunting because it looks like it's a lot of steps, but all it is a way to move towards that Bellman equation being true. All right? So I'll explain this word for word, and I hope you all will know how to, you'll all understand this based on the fact that you understood the previous thing. So we're saying that the Q value of some certain state action pair should be updated to be whatever it was before my estimate, so my old prediction, plus some learning rate alpha, we have some learning rate, of the reward that I just got, plus gamma times the estimate of the optimal future value. So this here, again, we saw this is V of state t plus 1. Right? So this is the value of being in the next state, whatever that next state is. And then you just subtract your old estimate because you want to find a difference. Right? So you're trying to say, whatever the difference is between my future value, this is the correct thing of what it should be, R plus gamma max A Q st plus 1A. We saw this. This is exactly what we saw in the Bellman equation, these two terms. And then we're just subtracting our old estimate, and then we're multiplying it by an alpha to get like a step in the right direction. So we're basically saying, what is the error that we had? We're going to multiply that by alpha, and we're going to add that to our previous estimate to move in the right direction to get closer to the correct thing. Now, we don't want to just set Q to be equal to this, because we're not sure that this is correct either, to be honest. So we're trying to do this thing called bootstrapping. We're saying we're going to assume this is true, we're going to update it, and then this also might be false, but we're going to update that later too to get to better and better values. All right, so this looks like a lot of math, but this is just the correct Q that we saw from the equation. You're subtracting the correct Q minus the actual Q. That gives you the difference of how wrong you were. And then you're multiplying that by alpha to get like some kind of step in the right direction. And then you're adding that to your old value to get your new value. All right, and now again, I'm going to give you a chance to stare at this for a second to see if it all makes sense. So you can actually write this code up, and you can have a Q function that's just a table, as we said before, and you can just go through each of the columns in the table, and you can update them based on this equation. You can take the max over the column of st plus 1, and then you subtract your current Q column, and then you add r plus gamma, and then you update that to your old value, and boom, you now have a closer and closer estimate. And you run that until convergence, and you'll have an optimal Q table. Yeah, Mark?
In that case, how do we figure out what the gamma and the learning rate is?
You don't figure them out. These are just things that we just pick as experimenters. So they're just hyperparameters. Normally people use gamma of 0.9, learning rate, just like in machine learning, of like 0.001 or something. But this is all up to you to change and tune as you see fit. The things that you don't change are the R, the max A, Q, ST plus 1, the Q, ST plus ST, AT, et cetera, because those are learned. Yeah?
What do you mean by repeat results when
Oh yeah, so this is just one step of the Q learning algorithm. You want to do this over and over and over and over again, and you're going to get your estimates closer and closer and closer to the true value of the Q, the true Q value. So you want to do this over and over and over again until your Q values don't change anymore. What happens if your Q value doesn't change anymore? What does that mean? If my Q of STA doesn't change when I do this update, what does that mean? It means I've converged, which means that this alpha r t plus 1 whatever is equal to 0, because this will just be the same. So this term must all be 0. And since this term is all 0, you can say that that means that r plus gamma max a q st plus 1a minus the old estimate is equal to 0, which means that this is equal to my old estimate, which means my old estimate was correct, so there's no point to change it anyway. All right. So now, finally, we get to acting. So now we have a Q function. You might be saying, OK, who cares? We have a Q function that's correct. So the question is now, if I give you a Q function that's correct, and I say you're in state S, what do? You don't know anything about the world. All you know is the Q. I give you a piece of paper with the Q values of all the things you could do, and I say you're in state S. What do? How do you act optimally? This isn't a trick question necessarily. So imagine I gave you right now a piece of paper that gave you the Q function of every possible action you could take in every single state you could be in.
Biggest one.
Pick the biggest one where?
The state that you're in.
Exactly. So you look at the state you're in, and then you look at all the Q values, you find the one that's the biggest, and then you take that action. Okay, so how do we say that mathematically? Well, we say that pi of S, and I'll explain what pi means, pi of S is equal to the argmax of A of Q of SA. Is everyone familiar with argmax, what that is? No? So there's two functions that are very important in computer science. There's the max operator, and then there's the argmax operator. So what does the max operator do? So if I were to say, what is max A of Q of SA? What does that mathematically represent? So if I removed arg, just imagine I deleted arg here. Yeah?
With all the possible inputs, what is the maximum value?
Exactly. So out of all the possible actions, what is the maximum Q value you'll get out? All right, the Q value outputs 7. That's the max A of Q of SA. Does that help me in any way to act if I know what the Q value is?
You know what actions you take.
Exactly. So you don't care what the maximum Q value is, you care what action led to the highest Q value. So argmax tells you what thing was the thing that gave you the highest value, not what the highest value was itself. So for like people that are learning computer science, if you have an array and you take the max of the array, what is that? What's the max of an array? If I say max, some array of numbers, what does that give me?
The maximum value.
The biggest value in the array, right? But if I were to say the argmax of the array, what does that give me?
The index.
Exactly. It gives you the index of the maximum value. All right? So is that clear? So the argmax here just says, what action gives me the highest Q value? Okay? And we call this thing a policy, and it's called pi because they both start with the letter P, and P was already taken, so they used pi. And so a policy basically says, what do you do at every state? So a policy is a function that maps from state to action, and it tells you, given a state, what is my policy of things to do? So you know how they say, like, honesty is the best policy? So that means that honesty would be the thing that has the highest Q value out of all the actions that you can take, and so that's the best policy you could take. All right, everyone clear about policy, Q, V, all these other things? Okay, so now that you've done this, you could follow any online Q learning tutorial, and you would be able to follow it completely. So starting here, you're all free, basically, you'll be able to learn any Q learning you want. There's so many YouTube videos that use Q learning to do really cool stuff, like learn how to walk and learn how to play games and all these things. And so I'm not going to focus on that aspect of it, because I'm sure you can all just Google it when you get home and you'll find a lot of really good resources. I'm going to try to dig a bit more deep and show you exactly how this really will work. So the thing that we were saying is this thing called tabular Q learning, all right? And so that's the idea that you have a bunch of, you have a table for every single one of the states, every single one of the actions. You have the Q value in it, right? So given the above table of Q values, what is pi of s? Well, pi of s is just going to be the maximum value in the row, right? Whatever number here is the maximum, you're going to take that column number action, okay? All right, so now we've gotten there, we've gotten that far. Can you believe that that was all just these two? Now we're going to talk about taking actions. So given a state S, we have an estimate for the value of our actions. Here we have state S, A1 is 3, A2 is 10, and A3 is minus 100. What action should we take? Let's say it in unison. A2 is the action we should take, exactly. So if you said second one, you're right. But what might be the problem here with just taking the best action? So remember, we're not sure if our Q functions are optimal when we're doing Q learning, because it's an iterative approach, right? So when you're trying to decide what action to take through the iterative approach, do you always want to take the best action? So before I know I saw your hand, I'll ask you this. So let's say you just moved to Amherst, all right, and you know that there's like 10 restaurants in Amherst, and you have no idea what the value of those restaurants are, how good their food is, how good the ambiance is, and all that stuff. You have no idea, right? What do you do? So you go to one of them, you say, okay, this one was, a 3 out of 10, all right? Then you go to another one, you say, okay, this one was a 2 out of 10. You go to another one, you say, okay, this one was a 7 out of 10, all right? Now, my question to all of you is, do you keep going to the 7 out of 10 restaurant, or do you try the 7 other restaurants that you haven't tried yet? This is not like there's no right or wrong answer here. I just want to know your personality, I guess.
Try a different one.
You would try a different one, okay?
Even worse. Even if the rating is surprisingly good.
Well, you don't know the rating yet, because the restaurants, you have no idea. There's no Google, whatever, that can tell you the ratings. So you would try it, right? So you don't know. So this is exactly the same issue that an RL algorithm has to go through. Because it's saying, I have all these actions. I'm not sure. I've not tried this action in a while. I'm not sure whether it's going to be good. So I might not want to always take the best thing available to me, because there might be something better if I just try it and see. So same thing with Q learning. You can only update a Q value once you've actually been to that state. So if you're never at a state, you can never update the Q value, so you're never going to learn how good that thing actually is, right? So given that, who wants to change their answer about what state they want to take, what action they want to take? It's completely fine if you want to take A2 still. Yeah, Mark.
I'd like to take A3.
A3, okay, very interesting. So you're taking A3, which is a really, really bad option from what you've seen. An estimate of it is that it's really, really bad, and that's completely valid, right? And now I hope, how many people would take A3? All right, good. So I would say that's about what, 5% of the room? Both of you, 5% of the room? So that's awesome, because 5% of the time, we could take A3, right? And then the other 95% of the time, we could take A2. So what I just described is this thing called epsilon greedy. So the idea is that you don't want to be greedy. You don't always want to take the best action, because there might be something better waiting around the corner. So now, let's say this is the idea. If I visited SA2 100 times, and that's my estimate, I visited SA1 3 times, and I visited SA3 only once, and I got an estimate of minus 100. Maybe the food at the restaurant that I got that one time was bad. Maybe if I go again, it'll actually be way better. So you don't actually know exactly the value of a thing when you try it once. You might want to try it many times to get a good estimate of how good things are. All right, so now, given this visitation count, who wants to take A2, A1, A3? All right, let's do a poll. So who would take A1 given this action, or given this set of visitation? There's no right or wrong answers again. Almost anything you say could be a possible RL explanation of it.
There's something wrong.
There's nothing wrong. I mean, okay, sure. So no one take this one. Okay, who will take A2? Okay, good. And who would take A3? All right. So the people that take A3, they're more exploratory, because that is a really bad option. Minus 100 is horrible. And yet, you've only tried it once, so maybe it was just a one-off, like you got food poisoning the one time you went to the restaurant, and maybe if you go again, it'll actually be great. Right? You never know. So this is the whole idea, is that we can act randomly every so often. So this is called epsilon greedy, where you basically just define a number e, epsilon, that goes between 0 and 1, And then whenever epsilon % of the time, you take a random action. Okay? And then the rest of the time, you take the best action available to you. Another thing is that you could prioritize performing actions that haven't been tried very often. So instead of just exploring randomly, you could say, I'm going to go to a thing with value, with the highest value, given that I've explored it less than 10 times or something, right? I want to take the best thing that I've not explored yet. Something like that would work. This is called count-based exploration. You could also, I like this, this is kind of funny, is that you assume unvisited actions are infinitely good. So this is called optimistic start. So you basically just assume that everything is great. And so you basically start with an estimate value for all the restaurants in Amherst to be 10 out of 10. And then you start there, you say, okay, 10 out of 10, I'm going to go to one of the restaurants. Okay, that was actually a 7 out of 10. Then I say, oh, all the other 9 are 10 out of 10, so you're going to go to one of those. And then you're going to keep going, and you're going to slowly shift the numbers down until you get a correct value for all of the values. You could also pick actions probabilistically weighted by their value. This is called softmax action selection. So basically you say, oh, if something is 2 times as good, I'm going to pick it 2 times as much, right? And so even if something is really, really bad, there still is a chance that you pick it eventually. So these are all 4 exploration paradigms for RL, and it's the idea that you want to explore new actions in as much as you also want to exploit the good ones. You want to explore ones that you haven't been to much yet, and you want to exploit the ones that you know are good. So this is actually the area of research that I focus the most on in reinforcement learning. Okay, so this is called the explore versus exploit problem. Oh, Nico, yeah.
How is exploration done, like, mathematically?
There's many, many different approaches. So the idea mostly is that you just augment your action selection step in Q-learning. So when you're trying to pick what action to take, you don't pick by just following your policy. You pick by either acting randomly or by doing one of these 4 things. So mathematically, that's all it is. It's just you change the one line of code in your Q-learning algorithm to when you're actually acting, because Q-learning has an agent actually playing the game. When you're actually playing the game, you don't always take the best thing that your Q table says. And so that's right. So there's no real big mathematical difference in how it works. There's more formal methods that include it with like a novelty weighting and all these other things, but that's too in the weeds. That's a good question, though. Anything else? Okay. So in machine learning, there's this big trade-off between exploring new options and exploiting knowledge, right? So you want to explore new options every so often, but you also want to take the options that you found to be good, right? So if we exploit too much, we might not find the best actions to take. If we explore too much, we might not use the knowledge that we have to perform well. Like, so if I already know how good all the restaurants are in Amherst, I want to eat at the best restaurant. I don't want to spend my time like trying all the bad ones in case they like somehow get better, you know? Okay, so this is epsilon greedy. We already talked about that. Yeah, so that's, now we put it all together. This is Q-learning in general. So you initialize some kind of algorithm, some kind of agent, and you do a series of these things called episodes. So episode is just like one lifetime of the agent from the beginning of the game or whatever to the end of the game or whatever. And so this is not very important. You all know each individual part of this. Now this is just putting it all together. You do, for every step of the episode, you choose the action from the state using whatever policy you derive from Q. So you're saying, or you can use whatever epsilon greedy you have here. So this is Nico, this is your question here. You just basically choose what action to take based on your current Q table. Then, given the response from the environment, given the reward you got, and given the new state that you're in, you can update the Q table based on this equation that we looked at. And then you just set the current state to be the new state. And then you repeat. And you do that over and over and over again. You take the best action you can, et cetera, et cetera, et cetera, and eventually you get a really, really good estimate for the Q values. So if you ever take CS, I want to say 383 here. Has anyone taken 383? I recommend it. It's a really good course. This is in the course. So if you look at CS 383, one of the problem sets is actually implementing this. So you all have a head start now. Okay. All right. So I think this is about as much as we're going to get through. A really sneak peek, since we do have like 4 or 5 minutes left before I want to show you a video of Q-learning, is that this is deep reinforcement learning. And the idea is that what happens if you can't encode all your states and actions in this table here? What do? Well, in the Sutton and Bartu book, they call this thing function approximation, where you can approximate Q of SA given some kind of neural network. So here's the idea. Think about if you're trying to learn to play chess. There's way, way, way too many states to actually write them all down in a Q table, right? There's 7.7 times 10 to the 45, and that, I'm sure that's an underestimate, different states for a chess game. And that's, I think, on the order of the number of atoms in the universe. So there's no way we can store that in our computer. right? So it just would be impossible. And the action space is even more high dimensional because you have, for every state, you have all the different actions you can take, which is insane. So the deep in DeepRL comes from, you guessed it, neural networks, where you basically, when there's way too many states or even continuous states, you can actually use a neural network to approximate the state value, V of S, and the state action pair value, Q of S. So you just have a neural network that takes an S and A and outputs a number, and then you can just train it just like you could normally. So you could train it with this thing called Deep Q Networks, which is a paper by Google DeepMind a few years ago. It's weird how far the field has come since the last time I gave this presentation. Yeah, so you can basically just do the exact same update formula and just train it using machine learning, where you just have the Q estimates and you want to reduce the error in your Q estimate as much as possible, just like you want to reduce the error of your machine learning model. We can talk about this more next week and actually go through the math. And then there's also another thing. So I guess there's a Google Colab here. Oh, it actually does work. OK, this must have been from last year. There's also policy gradient, which is another algorithm that we'll get to next week. But you can actually train using this math here, in case anyone's interested, and I could go through it, is a way you can train a policy directly without having to train first a Q value and then using that to update the policy. Which technically this is kind of doing in the loop, but yeah. OK, so here is, let me do this, if I can get this to work. All right, so this is now a Pong agent playing, or sorry, this is a policy gradient algorithm. Oh, what happened? When I plugged it in, it shut off my YouTube. OK. All right. Here we go. Sorry for everyone on Zoom. All right, so hopefully the video works. Yeah, I don't know why my YouTube has just not been working at all recently. It just like does this the entire time. All right, believe me, the video clip is a video clip of the agent actually playing the game correctly. Let's see if I refresh it, will it work? No, okay, my YouTube is broken. All right, well anyways, you can just Google, if you Google Pong, oh, is it working now? No, it's not working. OK. Well, you can just Google Pong AI, or you can Google Deep Q Learning or Q Learning, and you'll see a bunch of videos of people using these algorithms that we talked about today to actually play games. And I think it's super interesting, in my opinion. Yeah, OK. I wish the video worked. This is unfortunate. Donnie, could I use your laptop to play the video? Sorry about that, everybody. Thanks. So if we just do all right. So this is a Deep Q network playing Atari Breakout. Has anyone played Atari Breakout here? Yeah? So, oh. Why does that not work? OK. There we go. So this is after training DQN for 100 episodes. You can see this is not a human player. This is an AI Q function playing the game. All right, so you can see after 100 episodes, it's kind of learning, OK, I can bounce the ball off. After 200 training episodes, so 200 training episodes means 200 times through that outer loop in the pseudocode I showed you. You can see that it's finally learning to do this like weird like shoot to the left and right, and that kind of works as a strategy. After 400, it's kind of learning to intercept the ball and finding the correct way to hit the ball back. All right. So if anyone's actually played this game, you know that there's a really cool strategy to get a really high score. So this is where the agent actually learns that strategy, which is that if you tunnel through the left, you can actually get the ball stuck up there and then get all the points for the entire game. And so the agent actually discovered that strategy just by playing. Now obviously this game has way too many states to write out in a Q table, so you use a function approximator. But if you could have a Q table, this would be even more accurate. If you could write down the Q values for every state action pair, you'd have a perfect playing game pretty much. And you trained it to convergence. Yeah? So there's a lot of YouTube videos that actually do this, where you basically see agents learning how to walk, agents learning how to play games, and now you all know how it works. So I encourage you to actually try it. So Nico, for example, and Daniel, you worked on making a reinforcement learning agent last semester in the project, right? Do you have any words of wisdom? Did you enjoy it?
Very enjoyable.
Awesome.
Frustrating at times, but something that we did was it's called a Markovian decision process.
Mhm.
So you're only accounting for the current state and you're not accounting for previous ones, and the agent is choosing its action based only on what the queue currently looks like or what the environment currently looks like. Definitely challenging.
Yeah. So what did you actually end up getting out of it? What did you do?
Like as a final result, we had our agent able to solve a cube up to like 8 scrambles from solve, and it was interesting. It didn't necessarily just undo the scrambles. It also didn't see how it was scrambled, but it did figure out ways to solve it from there.
Yeah, and with more compute, I promise you it could have solved the entire cube, because people have trained with RL not only as solving a Rubik's Cube, but actually learning how to make a robot arm that directly solves the Rubik's Cube. So there's like even way more high dimensional of a search space. Yeah, so I really think that this is a very fruitful area for what you could do for your project, because A, it's a really hot topic right now in machine learning. A lot of networks deep neural networks, language models, et cetera, are trained with reinforcement learning. So it's a cool thing to say you know how to work with. And it's also really, really fun, because you can actually just make a game and play the game with these like AI systems, and they turn out to be really good, like much better than you think on actually playing these games. So if anyone wants any resources, I'll probably be sending out a couple on the Discord/email of like videos, code, examples, et cetera, et cetera. I also encourage you to just Google it. There's a lot of stuff online right now about Q learning specifically. And any questions that come up when you're trying to implement it yourself, let me know. All right, and thank you, everybody. Thank you.